Good morning, everyone. Thank you very much for joining our webinar. Please remember to switch off your microphones, and if you cannot hear me, please check your speakers. Make sure they are switched on. My name is Emma Trach, and I will be hosting today's webinar along with Larry Wren and the European sales team. The speaker for today's webinar, Plastics of Automotive Industry, is a well-known Mr. Tober Sun. The webinar will take approximately 1 hour. We will have Q&A session at the end. Okay, thank you very much. So let's begin. Ladies and gentlemen, Mr. Tober Sun.
Okay, good morning, everyone, and thanks, Emma, for the introduction. And we pretty much have all our European team over here. And today's topic is about the plastic usage in the automotive industry. Of course, we try to focusing on what Moldex3D can benefit in your design of your vehicle or your plastic part design and manufacturing. What might be the problems and what are the trends right now, either in manufacturing and in simulation. So this pretty much happened at the end of last year, 2013, and we see a lot of accident happen in this kind of advanced vehicle system, pretty much using fuel cell or batteries. So what happens is these cars are really advanced and state-of-the-art, and a lot of things are still not fully tested. Because sometimes during, because like these two fires, they happen during where there's a puncture on the road. So the falling object from the previous car just punctured through the cell module. So it's causing heat, the whole cell modules to heat up and cause fire. So these are a lot of things that it's kind of hard to predict, advance, and to design something, some mechanism around that particular important area. So above all, there are increasingly a lot of usage of plastics in this kind of vehicles due to the fuel economy constraint. So last year, we've working with GM to find out that how to improve the safety of the car. So this is one of the examples showing a battery module. So this is Chevy Volt, and they have a battery module. It's shown on the top left corner. And on the bottom, you see a picture showing the battery frame. So because of the easiness of these modules to get heat up, and there's either the coolant fluid flowing through the channels, and you have to protect the battery inside. So the plastic frames surrounding these batteries are really crucial, either in its dimensional stability, longevity, and if there's any manufacturing problems when designing or manufacturing this kind of part. So we partner with GM, and the key thing is to find out the dimensional stability. What's the warpage after demolding? Is there any way to reduce that? So if you see on the bottom right corner, there are two pictures. On the right, there's a infrared thermal picture showing the residual heat areas. So this is really crucial because these areas happen to be where the coolant fluid is running through to cool down the battery module. So any dimensional stability, any deviation from the spec is really important. So this is one of the benefit in Moldex3D can do in designing such kind of crucial and advanced power systems. So this is one of the examples that Moldex3D can do. So like these battery modules, when designers think beforehand. So when designing this kind of power system, they have to have something in their mind. How am I going to make this kind of coolant system? I use plastics or I use metals. So if I choose plastics, what might go wrong? So for Moldex3D, what we try to do is start to evaluate this kind of design at a very early concept stage. So either you are surveying the materials, whether you are staying with polypropylene plus glass fiber, or there might be some needs on the temperature, so you have to switch to nylon. Either of that, you can easily use the software to compare between the materials. What are their processing temperature range? What's their the thermal stability range? All these things can be used and thought about from the software, from the simulation point of view at a very early stage. So next we can move on to part engineering. There are a lot of design validation needs to be done at this stage, start from the concept stage. So right now pretty much a lot of structural components, under the hood components, and even the bumpers use a lot of fiber reinforced materials. If you have a fiber involved, there's always being anisotropic properties. So this is a very good stage when you can evaluate what is the part performance after you have designed what kind of process you're using. Then we switch to process engineering stage. So you can either select injection molding, or recently there's been a lot of compression molding process being used. So you can think of the geometry and shape of your product and decide what kind of process you can use. And at the later stage, we move on to manufacturing on the shop floor. So there are a lot of very realistic problems happening every day. How do I optimize the process condition? Is there what kind of defect I will encounter? How to do troubleshooting? So Moldex3D can cover pretty much all the range, starting from concept up to manufacturing, all the way inside this vehicle design cycle. So in order to fit in the cycle, we partner with a lot of softwares. So for the design stage, we partner with Siemens, PTC, and Dassault. So there are a lot of ways between the data exchange and the use of CAD file. For example, we can have embedded user interface directly inside this software. Also, we have other kind of modules that can do seamless integration. So switching the data from your CAD file up to Moldex3D is very easy. Or Moldex3D can work as a standalone module. So everything you need to talk between the CAD file and Moldex3D is just the neutral file format, like STL file. So this makes plastic processing, design and validation, and mold design very easy using Moldex3D. So after the the design stage has been done, we move to the engineering stage. So a lot of these process-induced defects or anisotropy can easily output from Moldex3D and feed into the software. So either you are using ANSYS, Simulia, MSC, Nastran, or Mark, or Digimat, or if you want to do dynamic testing on the Dyna, it's all possible. So this makes Moldex3D stand in a very interesting but pivotal position. So it can connect between the CAD data and link to CAE data. What it does is trying to make the most realistic plastic engineering information and sends back and forth between all these simulation tools or design tools that you already have in your company. So we also work. We have a long years of experience working for our customers. So you can see from this graph the OEMs and the tier 1 customers that we have. And today's talk is the beginning of a serious talk. So I think we planned in the following 3 months, maybe there are 3 consecutive talks, we will cover all these different components. So for the following talk, the next one, we will talk a little bit about interior, exterior, and optical. These components rely a lot on the cost reduction and quality improvement. And the second one, we'll be talking about the body and structural. So we will see a lot of examples of showing how to do the structural analysis, how to use Moldex3D's information and send into your engineering design tools. And the third talk will be talking about components inside the under the hood, or electricity components and fuel components, which relate to safety and reliability. So you will see some of the functions that Moldex3D can do to evaluate the longevity of this kind of product. So this year we pretty much grouped our modules into providing our customers different automotive solutions. So the first thing we care about is quality and cost. So later on you will see examples of showing how to use Moldex3D to improve product quality. And the second one is about safety and performance. And the third one is about lightweight future. So starting from BMW i3, people has already a lot of knowledge about what carbon fiber frame can do in the future, because lightweight will be the undeniable future, of course, but the how to make it fast, make it feasible, what are the processes that can be done. It's right now people are all experimenting, OEMs are finding ways to do that. And Moldex3D is keeping up with this trend. So we also test in our software a lot of different lightweight process capabilities. So we can also have that solutions for our customers. So talk about cost saving and quality improving. This is one example of our customer. It's the rent car, which has a lot of knowledge making a lot of electric components in the car. So this is the battery lead. So we can easily see from the benefit, we can judge it from a couple of aspects. First of all is the cycle time improvement. Of course, with each shortening of the cycle time, we can produce more parts in the same amount of time. And then it's during the design stage, we can also save a lot on the mold fixing. So usually you need to have need to fix the mold back and forth maybe 4 to 5 times. But usually when after using the filling simulation, you can drop down to maybe 3 times. So that's a lot of lead time in also improvement. And one of the most important thing is the product quality. So you can see from this chart, the rejection rate dropped a lot. So it's almost up to a half of the product. So we have 41% of the product quality improvement. So the yield is very high. And before, they even need to spend some time and money on the electrolysis dye test to see if there are any leakage because of the poor quality. But right now, since the yield is high, the quality has improved, they even don't need that test anymore. So they can dump this, so they can save even more money out of that. So from this example, you can easily see what kind of benefit that mold filling simulation can do when designing or manufacturing automotive components. So speak of quality, there are 3 major things that people care about. It's the warpage, weld line, and sink mark. So today we won't be covering all 3 of them. We will save it for our next talk, which is sometime during the April, and we will let you know, guys, the exact date after this seminar. But today we can take a look at how what Moldex3D can deal with weld line problems. So the first thing, of course, is to accurately predict the weld line location. So you can see from this graph, after you manipulate different gate locations, so from the bottom 3 charts, you can see originally it's a really large red line across the bottom side of this part. And after you manipulate the gate location, you can see we scatter that the weld line location around. So its weld line is inevitable because you have 2 gates and it's not a hot runner system. But right now you can see it's not a straight long line, it's not continuous, so it's doing less damage to the part if you have a structural problem. And further down the road, we can even scatter this around further. So you can see from the bottom right corner, you almost see no a straight consecutive line. Everything is pretty much scattered. So this benefits to the structural integrity, also benefits to the appearance. So this is another example, because sometimes the real case is a lot of things is that the mold has been fixed, the part design has been fixed. There's limited, you cannot change too much on the gate location. So what can you do? So we can still make a lot of adjustment just based on some tiny features or not so important features in the part. For example, for this handle lead, it's the back side of the part that we are doing a lot of changing, either on the boss shape or on the thickness. And what we're trying to do basically is to change. If you see the right side of the picture, you can see the red line and the black line. There used to be a visible weld line near that location, but through the manipulation of the thickness and the shape of some features, we can change the speed of the red and the black male front advancement. So by changing that, we can change the weld line location into a less visible place, and maybe by changing the welding angle, we can shorten the weld line as well. So this is something you can also do even if your design has been fixed and there's nothing much you can do about the geometry, but still you can use some of the change some of the mold tiny features to erase the weld line. This is another examples of showing that using different gate we can test on the gate design. So this is a front grille, and you can see from these 4 different designs we can have a lot of different combination of the weld lines. And not only on the location, we can also estimate the weld line temperature. So location, of course, we want it to be in a less visible place, but if the weld line temperature is too low, it's still doing a lot of damage to the structure. But if we can also raise that weld line temperature by making the 2 male fronts hotter than before, we still have a very strong joint in between and make them less visible. So if we're using fiber, weld line location will causing another problem. So this is showing one of the examples of what Moldex3D can predict about fibers. And in Moldex3D, we are really proud of our unique fiber orientation estimation theories. So we put a lot of efforts in predicting this kind of anisotropic behavior, almost really close to reality. So you can see this this male front is coming from left and right. There's a weld line in the center. Near that weld line location, the fiber is basically not following the flow direction, but perpendicular to that. So this creates a problem. For example, we can also show from this chart the green lines, the vectors suggest the fiber orientation. And the male front is going from the right-hand side, passing through that circle and joins on the left-hand side. You can see the fibers, they align almost in parallel. So during that weld line location, no fiber is intersecting, crossing that weld line location. So this creates a very weak area over here. And what makes it worse is this always happens surrounding the hole. So if you are doing some structural analysis, if you don't take this kind of anisotropy into consideration, you will falsely overpredict the strength of your part. But through this kind of simulation, later on you'll find out actually you did have a weak spot surrounding that circle. That's due to the fiber orientation. So back to the tensile testing. So you can see without considering the fiber orientation, which is shown on the top, you see the stress distribution is uniform. There's no stress concentrated region. But in reality, there's a weld line in the center, so you can see there's a really high concentrated area showing an 80 megapascal stress over that region. So we can say that without considering this kind of anisotropy, you will have limitation getting your structural simulation correct. So there are a lot of ways, of course, to get rid of weld lines. So this is showing one of the examples that Moldex3D can predict. So this is a hot runner sequential gating that's been used a lot to erase the weld line. And in Moldex3D, we have these unique features of showing the particle tracer. So you can see on the left-hand side, this hot runner opens first. So you can following all the particles and make estimations as it passes through your second inlet location. So this helps the designers a lot in designing what kind of gate sequential I should use. How do I know if the first melt front is already past the second one? So right now, of course, a lot of hot runner makers will insert a lot of sensors so they can predict that when does the first melt going past to the second. But during the design stage, when designing how many hot runner you are using, do you really need a gate controllable hot runner? So this is a very good tool based on your geometry, based on your actual melt flow, to define how many hot runners and how much you're going to spend in this investment. And of course, today we won't talk a lot, but we can also expect Moldex3D to improve your sync mark. So originally, you see on the top left corner, see two sync mark locations. They are slightly brighter in color. And gate location change might not do much help. And you might want to change your mold temperature. Of course, when you lower it, lower the mold temperature, the Moldex3D can capture that slight difference on the temperature and getting the estimation of the frozen layer correct. So once you lower the mold temperature, the frozen layer is thicker and the weld line is not so obvious. So we can get rid of this problem. So this is how in detail Moldex3D can do to benefit these problems. And of course, people all worry about the warpage. We will save it for the next time. But in this case, we see the tiny features, the groove that have been covered inside the part, change on the mold can help to eliminate that warpage a lot. So in this second phase, we'll talk about a lot of trends in the future. For example, the most important thing people all focused on is the lightweight technology. So you see, right now, a lot of things are manufactured through a lot of composite. So changing from the steel to composite, what kind of manufacturing process you want to choose, and maybe you want to even further estimate the cost of the process, the time it required to finish one part. So we will see how Moldex3D can benefit this kind of technique. So in Moldex3D, for the lightweight, we have all these four pretty much really trendy techniques right now. So either chemical forming or mu cell forming. You have fiber reinforced. You are using co-injection, which is a combination of fibrous field core plus a soft, more aesthetically acceptable skin. And also, you have a lot of gas-assisted applications also, especially for the car handles that you can use when doing injection molding. So Moldex3D can all support these kind of lightweight techniques. So this is one of the examples of the mu cell. Right now, the technique is still very new. You have to use the specialized equipment to finalize in making the supercritical fluid and to inject it in your resin. But we already see a lot of applications, and Moldex3D can help you during the design stage, verification stage, and also even on the troubleshooting stage. For example, here you see the bubble is too big, so it's like a burp on the surface. This is from the simulation. We find out that this is due to a really high temperature causing the cells to grow too fast and causing these kind of problems. So all these things can all be simulated and validated through the software. And during the K show last year, the BASF is pretty much trying to bring out the entire complete portfolio for their fibrous field product. For example, some are non-structural, and then with increasing length of the fiber, the structure just gets better and better. And even for some really demanding applications, you have a hybrid system between the composite and steel. So we already acknowledge this trend, and we find our customer was asking more and more and demand us to develop tools in this kind of high-end usage composite design. So in Moldex3D, we also roll out a complete portfolio starting from short fiber up to long fiber with the increasing up to a fiber mat compression. And even also we went to the RTM. For example, a lot of components in i3, BMW i3 is made by the RTM process. So a lot of these things, although the industry is still experimenting and playing, but we are, as the independent largest mold fitting simulation software in the world, we need to catch up with this trend. So we are also striving to develop this kind of tools for our users to evaluate. And this is one of the examples showing a glass mat thermoplastic material is pressed into the mold. So you can see it's not like your traditional injection molding process. Everything is compressed from the other side, and you can see how does it goes into those rib regions. And we also have the RTM module. So we can use other softwares as the pre-processing tool and import the fiber mat orientation, or you can define the fiber mat orientation inside our software, and we can evaluate the melt front, and you can see animation on the bottom right corner. Because there's a guide film on the top, so it flows faster on the top, then gradually sinks down through the Z direction. Because in this case, the D direction has a lower permeability. So we can also use the Moldex3D to evaluate the RTM process. And all the things, even all the kinds of fiber reinforced material, we still need a way to evaluate its performance. So like I've shown before, connecting to FEA software is very crucial. So these, but at the same time, the FEA software, if you want to get the correct results, you also need this kind of process-induced anisotropy. So here, example showing if you're just using a single material isotropic model to compare between an anisotropic one. So on the top one, you will overpredict your overestimate your the deformation. So actually for this part, it's already strong enough. So because you see on the bottom part, this part is injected, the melt enters from left to the right. So a lot of fibers are oriented following the flow direction. So it will make the part is stronger after you press it. But if you don't consider that, you will think the part is so isotropic. So during the prediction of the structural simulation, the deformation is actually higher. So if you think it's higher, you may increase the thickness and you may increase the rib structure. You are doing over-engineering. So this is something that we don't want it to happen because it's waste time and waste materials. So Moldex3D can provide you with the most accurate microstructure and make sure that you can get better results during structural simulation. So talk about fibers. we not care about the orientation, we also care about the fiber length. With the increasing of the fiber length, fiber retention is become more and more important. And also with the increasing load of the fiber. Right now, a typical fiber for nylon, pretty much you can go to 55% field. That's a common case right now. So on this really high concentrated system, can you also always have a really homogeneous distribution of your fiber? So we can also do a concentration analysis. For example, in this case, we show two different kind of product ribs. You have 1 millimeter rib and 0.5 millimeter rib. In this case, the red color denotes there's a high concentration of the fiber. So you can see in the 1 millimeter rib, the fiber can enter the rib without any too much problem. It's really homogeneous. But if you check on the 0.5 millimeter rib, because the rib thickness is close to the fiber length, a lot of fiber will get stuck in that entrance. So we can see on the right corner, there's a red region over here. And also inside the rib, you will see at the very beginning, you see a lot of blue colored area, which means you have a less concentrated fiber distribution over there. So this is a very valuable tool for designers to think about the rib thickness, because maybe the rib thickness is enough even up to the structural analysis, it's fine. But during the actual manufacturing, the workers, the technicians will always have troubles getting those fibers into those regions. That's not related to the material itself. That's not related to the process, but still it will trace back to the original design of the geometry. So that's why at the very beginning, we want to treat Moldex3D as a tool to cover the entire design cycle of the vehicle, because these kind of problems only can happen during manufacturing, but still people can use this tool to see beforehand during the design stage to take this into consideration. So at the end, we would like to conclude that during the entire product life cycle, Moldex3D stands between the design and the manufacturing. So we want to verify the design and assist the manufacturing of that. Okay, so this concludes the short talk of today. I hope we can give you a very beginning tease of what we will be covering for the following 3 talks.
Thank you very much, Tober. Now we will have the Q&A session. So if you have any questions, please type it in the chat box and we will answer shortly. Thank you. Yes. Yes. Hello. Yes, I can hear you. Mm-hmm. Mm-hmm. Go ahead.
Sure. Yeah. Yeah. Oh, okay. Okay. Thanks for the question. I think the automotive people can always learn from the aerospace industry. So aerospace, of course, is way ahead of us. Of course, they don't care too much about the cost and production time, and so that's why they can always have the best stiffness versus weight product. So what they're using right now, everything is pretty much about the carbon fiber. So I would say no matter what kind of matrix are using right now, even people are testing a lot of on the thermoplastic resins. So whatever kind of resins, polypropylene, nylons, or even some engineering plastics, hard to say, but inevitably the future of the car with the decreasing cost of the carbon fiber and the greater production volume. So we pretty much would say that in the next 10 to 20 years, we will see more and more carbon fibers being used. But through what kind of process, what kind of materials, what kind of joining technology? Because right now we are talking about carbon fibers. The joining, the fixing of them, say, for example, the BMW i3, they can make the whole car out of the not one piece, but make it just a simple geometry using a lot of because the mold can be very complex. But the thing is, it will make the fixing very difficult. So they still have to separate into different components and using a lot of joining technology. So we would see that if the joining technology is catching up very fast, it's all about the bonding strengths and what kind of things we're using. So if that's quite feasible, then I would say the carbon fiber will pretty much dominate the future development or choosing of the materials. Okay, thank you.
Are there any other questions? Yes, we can hear you.
So, are you talking about the, sorry, I want just to clarify the question about the material variability that you will encounter during the manufacturing? Is that the question? Yes. Oh, okay, okay. I pretty much so. Yes, this is a lot of problems people have right now. So when you choose materials, you pretty much can only rely on the MFI value. So we all know that feeling is very crucial, very important. But basically, when choosing the material, you have only this value to count out. So this is really not too scientific right now, especially after we have powerful simulation tools. So of course, during simulation, we cannot just rely on the MFI value. MFI value is just an indication about the viscosity at a very, very low filling rate, and it's not a reflection on your injection molding stage. So usually what we do is we will work with our customer. If they like to select the materials, we can do material testing and get a more accurate material property during the filling stage. Everything is faster, the pressure is higher, the temperature might raise during viscous heating. So all the things will be considered and needs to be considered to get simulation correct. So usually people will ask for suggestions about choosing the materials. So of course, the first step is of course MFI value. But the next thing we would like to do is to test on some samples to see whether during the new actual manufacturing process, even if you choose the similar MFI value, but if they perform very differently during a very high-speed filling, so it will still give you scrap, it will still give you a lot of filling problems. So to briefly answer your question, we rely on more information on the material, and this can always be measured in the Moldex3D lab. And actually, you know what? After 2 weeks from now, same time, we will have a seminar talk just focus on material testing capabilities within our lab, and how we use the material data in simulation. And of course, the host is still be me. So if you are still available after 2 weeks, I welcome you to join the other seminar, which will be focusing on material property measurement.
Thank you, Ali. The next question is from Pablo. The question is, can the software reproduce a RTM process with KZZ in 3D models?
Okay, so I think we have an expert here talk about so this is the fundamental difference between our RTM and other software's RTM. So because of course we have a 3D in our name, so unfortunately pretty much we do everything 3D. So in RTM module, we also would like to do it the same way to differentiate our function to other software's function. So yes, we also include the KZZ in the Z direction. We do the RTM process. And we also have the measurement capability inside our lab to measure the XX and YY and ZZ. So I think through the harness of all three permeability result, the constants, we can pretty much have a very good estimation on that.
And another question from Pablo is, what kind of FEM model is necessary, BLM or Tetra?
So if you are referring to the RTM process, yes, right now we can have like Tetra or Hexa. So right now it's not limited by the kind of mesh you're using. So we can use both. But since RTM is not a very high-speed injection process, so the key thing of using BLM is for injection molding. We have a very high transient velocity gradient near the surface. We have a very high temperature gradient on the surface. So that's why we will need the BLM. That's the tool, the weapon we designed to counter that problem. But for the RTM process, we don't have such kind of huge change on velocity and temperature, so we don't really rely on BLM. So I would say Tetra or Hexa is good enough to do the RTM testing, simulation.
Thank you very much, Pablo, for your question. And we are waiting for other questions. Yes, hello, please go ahead. Yes, we will share this presentation after the show. Thank you. We are still waiting for more questions. It seems that we don't have any more questions. Thank you all very much for joining our webinar. Have a nice day. Bye-bye.